There is a theory that says the Sun has a sister called Nemesis, which from time to time gets closer, destabilizes the orbits of comets and asteroids, and causes them to impact the planets. This star would be to blame for the mass extinctions that have occurred throughout the history of life on Earth. How possible is it for a star to cause this? And most importantly, is there a twin star of the Sun called Nemesis? Let's find out. Nemesis, the dark star, twin of the Sun. First of all, we must know how stars are formed. The origin of the stars is in the nebulae, immense concentrations of dust and gas. This matter gradually concentrates in different nebula areas until gravity causes them to collapse, forming stars. In the 1980s, it was suggested that perhaps the Sun was not alone but had a companion. That hypothetical object was named Nemesis after the Greek goddess of revenge. It was named like that because it would be responsible for the successive mass extinctions that the Earth has gone through, which would occur in cyclical periods every 27 million years. Richard Muller from the University of California, Berkeley proposed in 1984 that a red dwarf star located a light year and a half from Earth would be responsible for causing these mass extinctions. To test this hypothesis, researchers Stephen W. Stoller and Sarah I. Sadavoy from the University of California at Berkeley and the Harvard-Smithsonian Astrophysical Observatory in Cambridge examined radio waves from 600 light-years from Earth, a populated area by young stars in the constellation Perseus. This project, called Van Dam, allows for the census of Type 0 plasma luminous spheroids, or stellar babies, and those of Type 1 between 500,000 and 1 million years old. The results provided the discovery of 45 solitary stars, 19 binary star systems, and another 5 with more than 2 stars. The researchers stated that stars with characteristics similar to our Sun are most often born with a twin sister, with whom they form a binary system. The best example is Alpha Centauri, the closest star to the Sun, which is not a star but a stellar system of 3 stars. The 2 main stars are Alpha Centauri A and Alpha Centauri B, which have very different characteristics similar to those of our Sun. These 2 stars are gravitationally anchored, making them revolve around each other and have a common center of mass. Around these 2 orbits, the star Alpha Centauri C, popularly known as Proxima Centauri, since of the 3 that make up the system is the closest to our solar system. The name is true of the star Polaris, the famous North Star, which is a 3-star system. Binary systems of 2 stars are the most common in the galaxy. However, the Sun is one of the few stars that does not have an orbital partner. Consider that the Oort cloud is located approximately 1 light-year from the Sun. The Oort cloud is a sphere that surrounds the solar system with a massive concentration of asteroids and comets trapped by the Sun's gravity. According to that theory, every time Nemesis approaches the inner solar system, it disturbs the orbits of many of those comets and asteroids found in the Oort cloud, precipitating them against the inner planets and causing impacts and cataclysms. According to this theory, this would explain the age of the craters that many planets and satellites have, and also some of the mass extinctions that have occurred on Earth, which occur with a supposed periodicity. Is there evidence of the existence of the star Nemesis? Many may wonder, if the Sun had a twin sister orbiting around it, how come we have never seen it? Remember that although a star is relatively easy to see due to its brightness, observing it directly becomes somewhat complicated if it is pretty far away and very small. To understand this, let's take the Alpha Centauri star system as an example again. Although today we know that this system is made up of 3 stars, this discovery is relatively recent. Hundreds of years ago, it was thought that Alpha Centauri was a single star like our Sun, and it was not until 1915, just over 100 years ago, when astronomer Robert Innes, director of the Union Observatory in Johannesburg, South Africa, discovered that it was a triple star system. Innes was looking for stars close to our solar system to measure their parallax. This is the technique used to determine the distance to stars by measuring their apparent displacement in the sky due to the movement of the Earth around the Sun. During this period, the astronomers observed that the star Alpha Centauri appeared to move differently from other nearby stars in the sky, suggesting that it was composed of 2 stars orbiting each other. Over time, astronomers confirmed that Alpha Centauri is a triple star system comprising 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. This system's 2 most prominent members, Alpha Centauri A and B, revolve around each other, orbiting around a common center of gravity for over 80 years. The distance between the 2 stars varies from 11.2 astronomical units, approximately the distance from the Sun to Saturn, to 35.6 astronomical units, approximately the distance from the Sun to Pluto. For its part, Proxima Centauri orbits around the 2 large ones at a much greater distance, between 4,300 and 13,000 astronomical units. The duration of this elliptical orbit of Proxima Centauri around the duo formed by Alpha Centauri A and B is estimated at 550,000 years. Consider the following. The distance between Proxima Centauri and the 2 stars Alpha Centauri A and B can be up to 13,000 astronomical units, equivalent to 1/5 of a light year. In other words, if there were a planet orbiting around Alpha Centauri A or B, that exoplanet, the Proxima Centauri star, would barely be visible to the naked eye, since from that distance its brightness would be weaker than that of other stars, such as Sirius or even of the Sun. And we are only considering an exoplanet where Proxima Centauri is 1/5 of a light year away. The hypothetical star Nemesis would be 2 light years away from the Sun, a little beyond the Oort cloud. If it were a star similar to Proxima Centauri, from Earth it would be difficult to see that star since it would not stand out from the rest. It would look like another star in the sky, not like the twin orbiting the Sun. This star would have an eccentric orbit around the Sun, approaching a maximum of 1.5 light years from the Sun every 27 million years. This orbit will coincide with the cycles of mass extinctions that have occurred on our planet throughout history. The explanation for this is that although the star would not directly affect the Earth with its radiation, its gravity would disturb the asteroids and comets of the Oort cloud, sending them to the inner solar system where they would cause chaos in all the planets, not only in the Earth. Due to this, many of those asteroids and comets would obtain very close orbits to Earth and impact our planet in the form of meteorites. Although it is an interesting hypothesis, the truth is that the slightest sign of the possible existence of the supposed star has never been detected. So could the Nemesis star exist? A dark star. An explanation is that we have not found the Nemesis star because it could be a dark star, that is, a brown dwarf. Brown dwarfs are in a gray area in classifying celestial objects. They are bigger than a planet but not as big as a star, and generally do not have enough mass to initiate nuclear hydrogen fusion reactions at their core. As a result, brown dwarfs do not emit enough energy to be visible in the visible spectrum of light. However, they emit infrared radiation and are detectable by telescopes at this wavelength. This object would not be visible even with the most powerful telescopes, since it does not emit light. However, if it did exist, it could be detected with other observation instruments, such as radio telescopes or infrared signal detectors. In addition, a brown dwarf at that distance from the Sun would have enough mass to exert a gravitational tug that would disturb the most distant objects in the solar system, and thus could be detected by the instruments we have today. Other scientists propose that if it wasn't a brown dwarf, it might be a small black hole, but it too would exert enough gravitational perturbations to be quickly detected by our telescopes. Before we move on to the search of a ghost, be sure to stay tuned afterwards if you haven't seen our earlier release on Is Jupiter a Failed Star? We'll see what is true about the statement. The search for a ghost. Because it is almost impossible for a star or a brown dwarf to exist, much less a black hole, a few years ago a new theory emerged, which is taken more seriously in the scientific community. This theory suggests that Nemesis could have existed, and that it would have been a companion of the Sun in its first million years of life, but that later it would have separated from it and followed its path through the Milky Way as an independent star. This theory arose after studying the Perseus molecular cloud, which we discussed at the beginning of this video. The scientists observed many new formed stars remarkably similar to the Sun in this cloud. Applying mathematical models, the only explanation that fits to understand what can be observed there is that the stars are born with a companion and eventually remain alone. This explains what could have happened in the nebula where the Sun was born billions of years ago. It may be that the Sun was also born with a sister star, Nemesis. For some time, both stars coexisted and orbited one around the other until millions of years later, Nemesis would end up separating from the Sun, and each one would continue its path separately around the Milky Way. This would also explain why the Sun goes back and forth around the galaxy, rising and falling throughout its entire journey, as if at some point it had been anchored to another star of similar mass. For now, it is not known exactly if the Sun was a binary star millions of years ago, but we hope that future investigations of the universe will give us the answer one day. Also, we know Gliese 710 will approach the Oort cloud to the point of disturbing orbits and precipitating objects into the interior of the solar system. Although this does not mean that a cataclysm like the one that extinguished the dinosaurs will occur, it indeed gives us food for thought. The search for the twin sister of the Sun, as well as the exploration of other binary stars and brown dwarfs, allow us to expand our knowledge of the cosmos and our existence. Science continues to advance, and with it, our understanding of the universe around us. It's fantastic to know that the movement of a single star several light years away from us can cause a cataclysm on Earth, but that is what motivates us to continue looking so incessantly for any star that could endanger us, even if that star no longer exists. In all likelihood, this is a belief born in the late 1970s, when it was discovered that Jupiter radiates about 1.5 times the amount of heat it receives from the Sun into space. This may have led to the suggestion that at one time the planet may have produced heat by nuclear fusion. Heat that would then have been partially conserved by thermal inertia. But if this were indeed the case, how is it that Saturn, which has a mass more than 3 times less than that of Jupiter, emits as much as 2.5 times the heat it receives from the Sun? Indeed, it is impossible that a celestial body with a certain mass emits more heat than another with a higher mass. And in fact, the explanation for the phenomena is another. Jupiter's internal structure consists of several layers. Below the gaseous atmosphere, we find a layer of liquid hydrogen and helium, one of metallic hydrogen, and a solid core whose composition is still uncertain. In the first layer, helium, being heavier, tends to descend, pushing up hydrogen. This results in a release of gravitational energy and thus heat. In the case of Saturn, since it is farther from the Sun and therefore colder, the stirring due to thermal motions is less, and therefore the helium sinks more easily, hence the greater intensity of heat emitted by the planet. Jupiter is a very normal planet. Failed stars are quite another matter. But are we really sure? Is the difference between a massive gas planet and the smallest star we know really that big and unbridgeable? Although there is a minimum boundary below which we speak of a planet and a maximum boundary beyond which we speak of a star, in reality these boundaries are still being defined, and understanding the true nature of a celestial body is by no means simple. However, we know that the smallest known star in our galaxy is called EBLM J0555-578b and is a red dwarf belonging to a triple system located about 630 light-years from Earth in the constellation Pictor. Given its small mass, less than half the solar mass, such a star cannot develop high pressures inside, and so nuclear reactions triggered in the core produce only a modest amount of energy. Precisely because of the extreme smallness of their combustion, these stars have extraordinarily long lives. Periods on the order of hundreds of billions of years are calculated for the smallest. Since the age of the universe is around 13 billion years, this means that to date, no red dwarf has yet gone extinct. Since the surface area of these stars is very small, the radiation losses of the remaining energy are extremely slow, and so even once all the hydrogen is used up, a red dwarf will continue to emit an increasingly dim light and slowly disappear from view altogether, transformed by now into an icy, invisible black dwarf. In short, EBLM is a really small star, with just enough mass, according to today's models of stellar evolution, to trigger hydrogen fusion in its core. Its diameter is 120,000 kilometers, not even 1/10 that of the Sun, and even smaller than Jupiter's equatorial diameter, which is 143,000 kilometers. Yet it shines and emits light. So you immediately wonder why Jupiter, which is even bigger, has remained a planet and has not become a star. The short answer is this: Jupiter is larger in size, but it does not have enough mass to trigger the process of nuclear fusion and the transformation of hydrogen into helium inside of it. For this to happen, in fact, an object must be massive enough and hot enough for individual atoms to overcome repulsive forces and compact. And if this tiny red dwarf succeeds in igniting its nuclear furnace, it is because, despite its small size, it possesses a mass that is about 85 times that of Jupiter. Just the minimum value for a globe of gas to get to compress its core so much that it heats up to the point of nuclear fusion. Hang on a sec, guys, before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You will help us to make products of even higher quality. But wait a minute. How is it 85 times more massive than Jupiter while being smaller? And here the answer can only be immediate. It succeeds because of the incredible value of its density, which is 188 grams per cubic centimeter. And do you want to know why we call this value incredible? Well, it will suffice only to think that the density of our Earth, which is also the highest in the solar system, is only 5.5 grams per cubic centimeter, while Jupiter's is really very low, only 1.3 grams per cubic centimeter. All this means only one thing: Jupiter could only become a star if its mass suddenly became 85 times greater than the mass it possesses now. Is there any chance that this could happen? In the real world, absolutely not. But in the science fiction world of the great Arthur Clarke, as we shall see in a moment, it did happen for real. There is, however, a decidedly more viable route for Jupiter to become a star anyway. That is of trying to become a brown dwarf, namely a substellar object whose mass is insufficient to be able to trigger the nuclear burning of hydrogen, but sufficient to trigger that of deuterium, which is a lighter isotope of hydrogen. Astronomers believe that typically a brown dwarf has a mass between 13 and 80 times the mass of Jupiter. But what the precise boundaries are is still somewhat debated. Brown dwarfs, they may appear as planets but form as stars. That is, they collapse directly from an entire nebula of molecular hydrogen rather from the accumulation of material in the disk around the star. The minimum mass limit to be able to speak of a brown dwarf is therefore 13 Jovian masses, upon reaching which deuterium burning begins. Past 65 Jovian masses, on the other hand, lithium fusion also takes place. Deuterium and lithium, however, are two elements found in small quantities within a brown dwarf. So energy production is extremely limited in time, and the fate of these celestial bodies is slow and gradual cooling. We know of brown dwarfs with surface temperatures around 2000 degrees Celsius and others, evidently colder, that barely reaches 200 degrees Celsius. In short, if Jupiter wanted to settle for becoming a brown dwarf, it would have to increase its mass by only 13 times. And albeit to a very modest extent, it would begin to emit light and heat, and slowly manage to warm the planetary environment in its vicinity. Could it be done? Once again, the answer is no. Where could we find 12 other globes of matter as massive as Jupiter? As we mentioned a moment ago, Arthur Clarke left us something to write about this. Do you remember these words? All these worlds are yours except Europa. Attempt no landing there. Use them together, use them in peace. In the novel 2010 Odyssey 2, from which the film 2010 The Year We Made Contact was later based, Jupiter actually transforms into a star, albeit with the help of billions of alien monoliths that increase the planet's density beyond the critical point. In this way, the former gaseous planet begins to radiate energy, and it is thanks to this scientific miracle that Jupiter's 4 satellites suddenly become worlds ready for colonization by humans. Of course, this is just good science fiction, not least because increasing Jupiter's mass could have some unpleasant downsides on the solar system. Let's try to figure out which ones, imagining that we have somehow managed to increase Jupiter's mass by 85 times and start the nuclear reaction. Meanwhile, it is necessary to say that doing so would not, as one might think, also result in a disproportionate increase in size. As a result of the compression of materials towards the center, the diameter would in fact increase by only 20%. We would thus obtain a red dwarf 170,000 kilometers in diameter and 300 times less luminous than the Sun. And since Jupiter is 4 times farther away from us than the Sun, we would get an increase in energy here on Earth equal to only 1/5000th of what we receive from the Sun. Practically, we would experience no change in temperature. Instead, there would be definite consequences for the brilliance of the star, which would appear in our night skies 80 times brighter than the full moon. Which means that the night would be erased for long periods of the year, and this would have enormous repercussions on the nocturnal habits of higher animals, deprived of the ability to hunt or hide properly. Phytoplankton would suddenly be able to grow without interruption, changing the balance in the marine ecosystem. Stars would only be seen very few times a year, and astronomical observation conducted from the land would cease, as would the nighttime migration of certain bird species. But all this would be nothing compared to the catastrophic gravitational changes that would result from Jupiter's sudden transformation into a star. The greatest danger in the immediacy would not come, however, from the changes in the orbits traveled by the planets, which would be felt only over several centuries, but in the chaos that the enormous mass of the red dwarf would bring to the fragile balance of the asteroid belt. In fact, the asteroid belt is currently governed and held together by the very gravitational influence of Jupiter. If Jupiter's mass were to be increased almost 100-fold, the billions of objects that make up the belt, currently orbiting the Sun like peaceful herds of bison, would be transformed into a chaotic horde of crazed animals. Many would be drawn towards the outer solar system and would impact the surviving gas giants Saturn, Uranus, and Neptune, destroying and scattering all their moons. Others would be directed towards the inner solar system, where they would bombard and again reduce the rocky planets, including our Earth, to formless, nearly liquid masses. All the larger objects in the solar system would be devastated by the blows of this cosmic billiard gone mad, and over time the remaining planets would either be ejected or diverted into much wider orbits capable of circling the common barycenter of the two stars. All this would occur, of course, if Jupiter's change between planet and star were instantaneous. It would be different if the solar system had already formed a binary star system. In that case, all planetary formation and the evolution of life would have taken different binaries, and we probably would not be here talking about it now. Jupiter is therefore not a failed star. It never even came close to becoming a star. Even if it was a small brown dwarf, it was not meant to be one, and it never had the slightest chance. All the better for us. Don't you agree?